Now this next bit is on trig substitutions rather than trig integrals, and we've talked about this already. And what I'm getting at is the ones where we've got a square root and two squares, and we want to turn that into one term. So we make use of a trig identity. So if we get the sum of two squares, I'll do x equals a tan theta. If I've got a squared minus x squared, I'll do a sine or a cos, whichever one you prefer. And if it's x squared minus a squared, we'll do sec. And that will allow us to make use of the trig identities to turn the two terms into one term. So 1 over the square root of a squared plus x squared. Now you might recall this is one of the ones I said, oh, well, it's useful to memorize this one. Let's go and prove that integral then. So I would use the a tan theta substitution, which means dx is a sec squared. So subbing that in. So on the bottom we have a squared plus a squared tan squared, which would be a squared sec squared. Square root of a squared sec squared is a sec, and then the a sec cancels and we just get the integral of sec, and the integral of sec is the log of sec plus tan. Now we need to substitute back in, so let's draw up a triangle. We said x was a tan theta, so tan is x on a, hypotenuse turns out to be the square root. So the log of sec theta, well that'll be the square root of a squared plus x squared on a, plus tan theta, which is x on a. And you might be looking at it and wondering, hey, well, that's not quite what it was. And the reason is they're both over a. A is a constant number. So I could use my log laws and say, oh, well, that's minus the log of a. But the log of a is just a constant anyway. And so I just have the square root of a squared plus x, and then plus a constant. So that's where that particular integral comes from. All right, let's do this one. Yes, I know we could do this because I could create derivative on top for this one. But let's do it via the trig substitution. So I'm going to use sine theta. That means dx is cos theta to theta. So I get sine theta, cos theta to theta on top. Square root of 1 minus sine squared on the bottom. 1 minus sine squared is cos squared. Square root of cos squared is cos. The cos will cancel with the cos. I just have the integral of sine. Integrate sine. And we're back to minus cos. Draw up a triangle so we can substitute back in. So x over 1, not the hypotenuse, the adjacent side. Square root of 1 minus x squared. Subbing back in, I get minus the square root of 1 minus x squared plus a constant, a rather long way of doing that one. Square root of x squared plus 3. X is the square root of 3 tan theta. So the x will be root 3 sec squared theta to theta. Subbing into that one. Well, square root of x squared plus 3 becomes 3 tan squared plus 3. 3 tan squared plus 3 is 3 sec squared. Square root of 3 sec squared is root 3 sec theta. The dx was root 3 sec squared theta. Uh-oh, sec cubed. Now you'll recall from yesterday, sec cubed is the one that we're really going to enjoy doing because, of course, we do this by parts. We change the sec cubed into sec times sec squared. U will be sec. To u is sec theta tan theta. To v is sec squared. So v becomes tan theta. But we have 3 times uv, sec theta tan theta, minus 3 times the integral of v to u, sec theta tan squared theta. Now the sec theta tan squared theta we can rewrite as 3 times the integral of sec cubed theta plus 3 sec theta. The integral of sec theta we know, log of sec plus tan. But hang on, we've got minus 3 sec cubed theta. But notice the original integral, which is 3 times the integral of sec cubed theta. I've just drawn up my triangle ready for the substitution. Rather than moving the integral of 3 sec cubed to the left-hand side, I haven't done that because I'd just be moving it to the square root of x squared plus 3. I'm substituting it because we have said the integral of the square root of x squared plus 3 is 3 sec cubed theta. So I have substituted in for the integral of 3 sec cubed theta, the square root of x squared plus 3, which I can then move to the left-hand side. I do it that way because I think it would be very easy to make a mistake and go, oh, let's move this to the other side. Now I've got 4 times the integral. But I don't. I only have 2 times the integral. So now I can move it over. I get 2 lots of the integral of x squared plus 3, and there's our integral. Mind you, whether we leave the log like that, or again we notice there's a constant in the bottom, so I could just absorb that into the constant, which I did. I've grabbed the exercise out of the old Patel textbook because the Cambridge one doesn't really have one on this specific thing, but I just think it's a good one to have a bit of practice with. So I photocopied that, I popped it in the back of the sheets there.